Smart. So I'm going to walk through a couple of different things. We're going to start with some of them that we've actually done, we've implemented. This is some historical data, some current active products, and then we'll also introduce you to a few future ideas kind of along the lines. I'll show you what he was referring to in the blast capability in actual form. So demo yet not real demo. So this particular example shows the host CPU processor. So when we first came out with this technology, we started getting people interested in it. We didn't have a good way for someone to see it in action. So we'd hit go and they'd see results and we're like, well, that's cool. Then we hit go and they see the faster results and like, well, how do I know that didn't run in the CPU? We actually had them put their hand on the heat sink of the processor during running it with the processor running. Then we had them put their hand on the heat sink of the processor when we ran it in the drive and it stayed cool. That was our demo at the time.
A Band-Aid, right?
Yeah. We were carefully didn't push too hard on the heatsink. So what we were able to do is our team came up with this GUI. So here's your host CPU. Over there are the 4 ARM A53 application processors and their CPU output during this process. So you can tell this is a bit older. This is one of our first demos. It was when Bush took over from Clinton. So what we're going to do is this is an output window for each of those 4 drives that are running these subprocessors, and we're going to train and infer and do facial recognition, but we're going to do it within the drive itself while the host sits here and just waits for the output. So as we run the demo, you can see we're loading images into the database, so that's a little bit of work being done by the host. You can see the drive the last drive we're programming with data. Now we're going to kick off the actual processes to run in situ within the drives. You can see all 4 of the drives are running at 100% processors, and you'll start seeing files output that they've done the facial recognition to and identifying who's who. But at the same time, down here on the bottom, the host isn't moving an inch. So she can be off doing whatever she wants, he or she, whatever you want to call it. You got to be friendly to the market. The CPU can do whatever they want to do while they're waiting for these results. But then you can see we can now go through all the different drives, have different files on them. It's all different data. They ran concurrently and still came back, and we're actually able to use that tool to identify every person in the images. So, and you'll see that there was even an example where it grabbed the wrong person. We didn't rewrite the app. We simply ran the app local at the data source.
So the windows there are effectively a file directory showing
exactly.
Of each of the drives as it creating.
Each one of these are independent. This is drive 1, 2, 3, and 4. All have unique data sets. They're all outputting the appropriate pictures or results that the host needs.
Yeah.
So we're able to do it simultaneously and concurrently. So back to kind of the CPU, can we keep up?
Right.
One of the biggest things that we fought with, and you saw a lot of other presentations and you mentioned about things like millions of IOPS, it's all about people have been trying to move the data faster because they're not doing anything with the data intelligently. I don't have to have faster than A53 processors, and I don't need a Gen 5 by 16 interface if I'm only moving 4 files instead of 4 terabytes of files. Because right now everybody's thinking, I got data in a storage locker, it's in the back of the locker behind everything else, I got to move the entire locker out to find what I'm looking for. We're saying no, that needle's hiding in there, let's just hand you the needle. It doesn't matter how fast the interface is because I'm saving you so much time on the transit work that you're doing to get that done. So one of the biggest examples we've had, and we've had the luxury of having Microsoft on stage with us, so I'm going to walk you through kind of the research project we're doing. They've been working on a project for 5 years called FlashSoft. They have a problem with scaling an image search process. They tried it with standard SSDs, they tried it just using GPUs, they've tried it doing with it in memory platforms, a la NVDIMM, whatnot. They were actually able to get the solution they're looking for using the in-situ processing with our SSDs. So what it comes down to is they use a tool called FACE, Facebook's AI similarity search. It's open source. You can go recode it. You can just download it, use it as you want to. But when you have 10 million images or 1 billion images, you start to get into scale problems. But what about when we get to 1 trillion images? So I've got 1 trillion different images sitting out on a database, and someone goes into Bing and says, I want to see a picture of a hot air balloon. And we know that back in the day when Google first came out, they're like .0000, how fast they can respond. It's becoming a problem to get actual results or relevant results fast enough. They can still give you fast results, but it may be further and further away. So this concept is built on the idea of an approximate nearest neighbor neural network.
Hey Scott, real quick.
Yes.
Are you guys working with any gaming companies?
Not yet.
For faster processing of the graphics to recall stuff?
No. There's opportunity there, but we haven't gotten to that point yet. So my son asked that very same question when he got his Alienware platform. Can I put your SSD in my box and make it work faster?
Yeah. Want it in my Xbox.
Yeah, there you go. If they put an NVMe interface on it, maybe we can make that work.
Luigi, if every vendor gave you every option you wanted for your Xbox, you'd need 510 of AC.
Okay.
That's true.
I'll take it.
He would install it for his.
He would. He would.
I would install that.
Put a
for
big
my
block of
phone.
dry ice on top of it.
Exactly. So
Just wanted to ask, Kevin, is it? Can you go back on one side? Is it clear what we're trying? What these companies are trying to do there? They have a mega data set, and then comes a query. It's okay. What are the pictures in this data set that are similar to that one? And from that, they can infer a lot of stuff because the pictures in the data set have a lot of metadata associated to it, location, date, and the actual content and everything, right? So
They're having to do a trade-off, and to basically meet their goals, that trade-off is one that doesn't necessarily really harm them so much, but it does harm those doing the search, and you guys mitigate that, allow them to scale much further without making the compromise.
Even to the extent that you can do a rough search in all the SSDs and say, deliver everything that's 80% likely to be a hit for the main processors to do the refinement.
Exactly.
So that the detail is working
that
on a
is
much
exactly
smaller
what
data
we
set.
have done.
That's correct.
And let me just say, and that's a perfect example of something that dovetails into what you just said. I mean, think about all the prediction you can do, all the offsetting, all the pre-rendering, all the,
I think about it because I remember when we went to I went on a tour to SuperNap and we went by the EA Call of Duty servers and they were just screaming. And I was like, well, if you could access that data faster and you can process it ultimately faster, it's going to provide a better experience.
So we've knocked on the doors at our neighbors down in SoCal Blizzard and a few other places like that to start talking to them on just even the rendering on the online gaming version of it, let alone the localized platform.
Yeah.
Just saying.
To make one.
So the
ahead.
process that they've implemented with FlashSoft is not just the ingestion of 100 or a trillion images, but building the structure to be able to query it with another image. That's the kind of stuff that's being done by the NGD solution?
Yeah.
That's right.
Yeah, we're going to detail that. Yeah.
It goes to the details.
Yeah. So I'll walk. So this was a nice little animation that our friends at Microsoft put together. So your query, you pull everything out of the drive. You have to scan, filter, and report it out. So you're completely emptying your storage locker every single time. And if you've got a smaller memory footprint, you can only fill the memory. You have to flush it, refill it. Then you run into a timestamp problem. You can't make the user wait that long. They'll time out. They'll say, oh crap, I got to hit refresh on the browser, whatever it is. So what they found is, if I go back and make it run the right way, they weren't getting enough spare processing power. So companies like my former employer, sorry, I just tapped on the mic. My former employer tried using what was left of the resources in a standard SSD. It just wouldn't work because you hit contention. That's where we get the consistency problem. Then you have to worry about, as he mentioned, the seamless programming model. They found a customer that could provide them a drive, but every time they wanted to change, they had to go back to that customer and ask for the change. And then, of course, not everybody had product just available on the market. You had to get specialized product, have to add permission, all that kind of fun stuff. So what we did is said, fine, we'll just take and move the filter and scan. We didn't move all the files, but we sent the files they needed, to your very exact point, Howard, the 80% rule, back up to the solution to be able to make that work for them. And I didn't know that was still active. So if you look at how the FACE platform or most neural network platforms work, you have to load, index. Every time you add a new picture, you have to use the memory just to do the indexing, let alone the actual images themselves. Well, we've moved that application down, so as the images are written, we're auto-indexing inside the drive, so there's no retraining, no anything else being done by the host. It's being indexed and trained into the neural network as it's being written to the drive. So when you want to go back to put the resources back out, your number of process steps is substantially reduced. Now, to the point about can we be faster than a host processor? No. And if you need to do stuff in memory, you're still going to do stuff in memory. If you need to do GPU acceleration, but if your data has already been stored or needs to be stored to be analyzed, then we can add value there. So we're going to store the bits, then process the bits and send them back out. We don't have the capability to make NAND any faster than anybody else can. And you could do this with Optane. We could throw persistent memories in here. Our controller's capable of handling those types of architectures, but there's still stuff that in memory is
Okay, so you offload part of the process, not everything, which is
the appropriate processes.
Yeah.
So their results are shown here, and the initial results say that if they use the host only, and if you look at it, this is from an application perspective, how many queries they can accomplish per second. With 16 drives that they already have to have in the system to store the database they need, they saw a 4x improvement. So all we did was help them by using the storage they have already paid for to do something more for them. Now, this is a really
Bought
cool
your
fun.
SSDs before planning on doing in situ processing with them?
What?
Never mind. Just snarky. It's not worth explaining.
I love it.
Is the device, you call the device an ISSD, is that?
This is what they called it, an intelligent SSD. So
That's what they called it.
I left their logo on it because I wanted to give them credit for building the slides because I'm a good marketing guy, but this guy had some more fun with his graphics than I did. So, so now let's look at it from a time perspective. So this is what another point Vladimir brought up. So this is looking at that same set of drives, not in queries per second, but how long it took to finish the process. So with a single drive and a single host and a small data set, if I blow that up, you can see that the host is going to win. One drive, small set of data, it fits in the memory footprint, the CPU is just going to kick my butt. But as the database grows and as I add more drives, I hit a crossover point where now every single one of my drives is added to the system, has a consistent response time because they're running in parallel, even though the data set inside each drive is 8 or 16 terabytes. So from a process time perspective, you see a significant benefit to the end customers. So this is talking about at-scale data center use model. So at 42 seconds versus a half a second to process data for that particular thing, that's a huge 500%, 500x type improvement to that user. And if you're talking tens of thousands of us searching Bing every day, those seconds count.
And why did the number of images matter from a scaling perspective? Because just on the amount of indexing that's required to handle 1 trillion images versus 1 billion.
The number of
because you have to do a search on the whole data set. As you're splitting it over different SSDs, and each SSD is finding the nearest neighbor.
Within that space. Yeah.
That's exactly what you said. So if I'm looking for the 10 nearest neighbors and I have 10 SSDs, I will have 10 times 10 results. Those go to the application running on the host that will take 100 results and take the 10 best. That's exactly what we're doing. So we're actually working together with the CPU to augment the whole process of the system. And let's be fair, the way I like to present this is that we suck here. And it was horrible when we first saw that. We're actually holding the whole system back.
Well, because you're doing the work on,
because
because you've got free Xeon cores, and you're doing it on those dinky little ARM cores that you have.
Yeah.
Of course, that takes longer.
Exactly. But as we add, and now the CPU is capable of doing is free and is capable of doing a lot more. And as we add more SSDs and grow the database, you can see that consistently we maintain the search time, and it helps the CPU do more stuff, and then we don't suck anymore.
Scott, your text is small and I'm old. That right column is one host and 16 SSDs, right?
Yes.
Yep.
But
Okay.
you'll see that no matter how many SSDs that we add, our response to the host system is exactly
That's not-
0.533 seconds.
That's not where I was going. At host plus 4 SSDs, time is roughly equal.
Correct.
So to get the same time, they would need 4 times as many servers.
Correct.
That's correct.
Yeah.
And
be able
that's
to do the
the
exact-
challenge
I'm
of
just giving you your marketing lines. Scott. It
Appreciate
costs a quarter as much.
Exactly. TCO is a big picture.
Good thing this is
guy here.
recorded so you can go back.
I will. I'll give him. I'm going to quote at Deep Storage Net.
It was something else you said a minute ago, because this whole time I've been thinking it in terms of there's data on these drives. We realize that there's an operation that needs to be run, and we do whatever work we can do on that data to essentially make it easier for that next stage of the data. But what you mentioned was having pre-knowledge of what actions you were likely to take on that data, and actually doing pre-processing on those images as they're stored. Did I understand you right?
Based on which type of application you're
Correct.
running.
Yeah, I mean,
This
you'd have to
particular
know.
application-
You'd have to have a lot more information
Yeah.
about what you're doing.
So
but if you did know that stuff,
Yeah.
you're basically pre-sorting before sorting's the wrong term, but preconditioning,
Yeah.
right?
That's right.
For this type of an application, absolutely, we have the capability to do that because that's what this application is doing in host memory. We're just doing it locally in the drive buffer drive memory.
That's another big thing.
We had this conversation already, but actually, when we see your software stack around the piece of hardware, why don't you have also a serverless computing framework somehow? One of the many, because instead of having all the data in the disk and then start the process manually or with a cron job or whatever, every time I put something, I want the processor working for me. And,
So
Correct?
yes.
Yeah.
So we have one example that we are not showing here. That's actually pretty cool.
Okay, well, go ahead.
It's we use TensorFlow and we trained it to recognize documents like a scanned ID card, a scanned,
Passport.
whatever,
Driver's license. from
driver's
different
license,
states.
whatever it is, and just for fun, we just start moving those files there, and then we wrote a script that, depending on what TensorFlow tells us, we move the file to the right folder. So this is the kind of example where if you have this, if you have an application that runs in the background constantly saying, oh, there's something new here, somebody uploaded a document, I'm gonna take care of it using TensorFlow and so on. That's a perfect example. So yes, it's all possible because we do have an operating system that's running constantly. But you have to write that application, right? You have to write it in that way, but it's possible.
Actually, with the image search time, I could see that being useful in the systems that I hate the most, in the toll systems. They're constantly snapping images, and they got to run queries against plates and so
Exactly.
forth.
That's
and
right.
Yeah.
That's
There's an SM.
example coming up.
I must have got a sneak peek.
Yeah, I know. So, exactly. So this is an actual video demo because I want to show you some real results. The beauty of this is going to be a single drive example, so I'm not even doing multiple drives. It's a one-on-one. This is running face on one of our current prototypes. This is running the same exact application but using the host system reading out of our drive. So it's both of them are our drive. One has it enabled, one has it disabled. So what we do is we've built a GUI that we can upload any image of choice that we want, tell it to update to the system, write it to the file, and then go do the inference and response. So in this case, we're going to upload a cat as it walks through, and you see we're going to upload this nice black and white cat. And we're going to tell it to go kick off. So we're kicking off both sides simultaneously. This is with the in situ, the other side is without. And roughly about 10 seconds in, because it's a single drive running on a smaller subset of data, I get a response back. And you can see here that it's going through and looking at all of the, let me get over
What do
here.
you need?
I was going to try to pause it. Nope, it didn't pause. It keeps resetting.
Yeah. Go ahead.
I can overcome the power of the computer. So what I want to highlight here is it's finding images of partials of cats of different colors, for example. And you'll note that the size of the search bar over here for the scrolling distance as we go through it, there's a lot of images it's found, and they're all unique images. So go ahead and hit play again. So we can scroll through, and you'll see that it's finding all of the different possible pictures, and yet we're still waiting on the other side for it to come up. So there's an example of a blow up of that type of thing, because I'm a marketing guy, I make it look pretty. Now at the bottom, you'll see the timestamp here. We're sitting roughly about 40 seconds in. If I scroll all the way out to just about a minute and a half, another full 90 seconds later, I just got response back from the host-only system of that same drive. And then you'll note that the number of images found is significantly less because I'm loading DRAM, flushing DRAM, and you'll catch right there that in the response that came back from the host, I have a duplicate image because it's pulled and reloaded the same DRAM platform multiple times. So even though I have fewer images back, I'm getting duplicate images from the response. So to the point of the value of the response of the data is just as important as how quickly you return the data. We don't see the same duplication over here because it's running so quickly in an in situ process.
So Scott, in the prior graph, you showed that up until 4 or 5 drives, it was roughly better to do it on the drive directly rather than do the computation in situ in the drive. So you mentioned that this was a single drive comparison.
This is a single drive
I'm trying to understand how it was quicker in that situation.
So this also has to do with the server. This is running on a desktop system with these guys plugged in one for one. So I'm not running at speed.
Oh, okay.
So I do have the equivalent of basically like a SATA drive versus an NVMe drive in the performance characteristics. And I apologize, I didn't clarify that at the beginning. So
and part of it is on me. In that previous example, I asked the team the toughest configuration possible to have that appear so that we can still show that as we go. So Face is such a complex application, you can make it easier or not. So we made it purposely tougher there so that we can see that, okay, in the beginning, in some configurations for some data set size, the size of the descriptors and so on, it's harder, right?
Yeah.
But yeah.
So then we've talked a lot about it. They mentioned the license plate. This is kind of the toll concept. So this is a slightly different take on this. And right now in this particular instance, I'm not looking for it to be necessarily substantially faster, but just more efficient to run in place. So you can see we're actually IP'd into an individual drive to run this app. We're not using the host resources at all for this process. So what we're doing is we're going to run a demo where it's going to go through, and we've got a preloaded image database, and we want to find and identify a specific car. So he sits here, looks around, and I click on the car, and then I'm going to go use this off-the-shelf containerized product that we downloaded directly to the drive over the IP address, and we can identify a given vehicle. And you can see the response time is very efficient, very fast, and very accurate for each of these particular drives. And then we can also add new images to it, so we can pull images off of our alternate drives within the system. In this case, he's done it a few times, so he keeps relabeling it so that we always know it's a new image going into the drive. Send it up into there, it pops itself into our database and is able to be recognized from a license plate recognition.
So you have like a serverless processing kinds of solution?
Yeah.
Yep.
Or the server, in the case of the new edge gateway, to be very light server type. So the CPUs are not hefty CPUs because it's limited.
So
this is an edge type environment.
Yeah, but if the data shows up, then it actually performs a service? Is that how it would work? Or?
Yeah,
Yeah.
it can, from that perspective, yes.
So you can imagine some of the newer edge gateway coming, they are pretty light. They are almost the same size as a small laptop. It has a CPU, the host CPU in it. It has networking as well as a lot of storage. So whatever can augment that host CPU, it becomes very powerful.
And the beauty of this one, again, we didn't do anything to the app. We didn't have to use we didn't have to use even any kind of migration of tool or reprogramming of the application, because it was a self-contained Docker that was able to drop right into the Linux OS on the drive. So, and I happen to choose this one just because it's always fun to talk about alcohol when you're in a room full of nerds, geeks, and dorks. So another example, if we think about object tracking, so this is my buddy and my biz dev guy in our office with that wall of patents that they mentioned. Historically, if we're looking for something when it comes to surveillance, we have to identify it with human eyes, find it, and then you have to worry about how to track it from camera to camera, all those kinds of things. So some of the future tech that we see going on with object tracking is how to do stored object tracking and then be able to do historical searches of that tracking across multiple cameras of that tracking. So we actually ran a little demo, and I've got it. It should run. Is it going to run for me?
Yeah.
Okay. So you can see our happy engineers because they actually got it working. This is 3 independent cameras plugged into a 2U server. Again, the CPU's not doing anything. We store the file, and 2 frames later, we've identified it and tracked it. So there you can see there's a little bit of a delay. This is near real time. It's not as fast as true real time as I'm walking into a building and it identifies me, because they're not storing that data, they're just using it for instant recognition. This is now a stored, identified file. We're still able to keep up with the person moving at frame rate because these are HD webcams, but you can see there's a tiny bit of a lag because it's near real time. But now I can historically search any one of those streams. And in theory would be I could set these things up in a rotunda, have someone walk around the room and then be able to recreate the file, all using in situ that shows them walk the loop in the room.
You can use that for like shoplifting in stores or airports.
Yeah, so we did the keynote a couple weeks ago at the big Flash Memory Summit show here in town. I used the idea of a lost girl in a football stadium full of everybody wearing blue and orange, because I'm from Boise. So everybody's wearing blue and orange, she's in an orange shirt and she's lost. How do you find her?
It's not Boise?
Boise, yes, we had that conversation. It's a C, not a Z. Boise. But yeah, so those are perfect examples of where you can use this type of technology. And again, this puts it kind of almost in that classification of fog, right? Because you're not necessarily just at the edge, but I don't have time to send this all the way back up to the cloud server, especially if there's some kind of time requirement around it. So being able to identify, find, and respond back with that kind of data using the drive itself to give you that analysis back.
There is a airline that's implementing that in going in and out of the country. Are you guys working with them on that, or?
We've had a couple conversations with several airlines and some companies supporting the airlines, so it's just ongoing work. We're very excited about the number of POCs. Will be even more fun when we can do talking about logos. But I was also told there are absolutely no NASCAR slides in this presentation. So, do you have any other comments? So those are things we're already doing. We've already done. We have partners for them. One of them, of course, Microsoft Research. We've got a lot of other opportunities out there. He mentioned Blast, and so this is a 3D rendering, and it's actually a bunch of slides I turned into a video just for fun. Percent improvement based on the number of cores added to the system. So as I throw more servers at it. And then in the alternate direction is throwing more drives at it as I'm storing the database. So the database size is going to start at 150 gigabytes, and it's going to grow. And as you see it growing, you can see that we're getting it continually improves by the number of cores, but as we get a larger and larger database, the amount of processing improvement due to the drives in the back gets faster and faster to the point where we've got it out to where we're getting a 100% increase in the performance of this protein sequencing application, and we've done nothing to the system except for use multiple drives to store a very large database.
Well, you have added a whole lot of cores. They're just in the drive,
Exactly.
not in the processor.
60 times 4, so 240 extra cores. And this is a perfect example to show how we can see that value of the increase of capability just by using your storage more intelligently, by moving the compute into the storage devices as well. So this particular one, I call it future because we've done it up to 16 drives today, and we can use that data. That was the early on data. This looks very, very clean because it is predictive of what we can get to based on how linear all of our responses to our scaling of our drives has been. So I wanted to make sure that we highlighted this is what can happen. Another example is talking about content delivery. So we have a partner here in the Bay Area that's working with us on this concept, and the idea about this has to do with security. So back to managing keys and things like that. Whenever you're doing encryption, all the encryption for all of your drives in the background all have to run through the one CPU. So if I got 24 drives, 48 drives, 96 drives, all the decode, the key management has to be managed by the host compute and memory for all of those drives. So I've created a pinch point on the encryption engine because the engine's running in memory. And so when you end up getting the data written back and forth, I can certainly encrypt in the drive, and I have an encryptable engine in the drive, but to be able to get the keys and do all the decode at the host side is complex because I have one spot to do it. And also you're now sharing keys across all of those buses to all of those drives. And then when you're ready, of course, the host memory is going to deliver to the NIC. So I've got, again, treating the data as data. All of the processing is done up here, but all the drives have to go through one root complex effectively. So what if we think about it a little different and we actually move that encryption algorithm into every single one of the drives? Now, not every drive has the same key. All the drives get all the keys, but they're stored once. They're never looked at again. They never leave the drive itself. And because each drive is running in parallel, it doesn't matter if I have to check it against 48 keys. I'm still doing it much faster than checking against 96 or 128 keys up here. And you do all of that data management in the drive memory. And then, of course, at the end of the day, we have the capability to actually deliver content without the host in the way, directly over the NIC.
So to add to that, so all the SSDs in the board so far, they have the encryption engine for self-encrypting. They encrypt on the way in, they decrypt on the way out. So what we have implemented is a special mode of the AES 256 that other than doing encryption on the way in and on the way out or encryption for the data address, we are also doing encryption for data in motion. And because we have the in situ, we can also do the key management inside. So in such a system, other than the drive is encrypting on the way out, when you have 16 of them or 40 of them in one box, one server, you can actually eliminate number of the servers and bring the total footprint to a much smaller footprint.
Yeah.
I did have a question on the NIC capabilities of the drives. At what point does you have to talk with the network admins? Because if you add in a bunch of drives and they all get their individual IP addresses, what challenges have you seen with network admins and firewall rules and so forth, as well as attack vectors?
So I let maybe Vladimir, it's more qualified to answer that.
No, to be honest, I mean, we haven't gotten to this point yet. We know it's a challenge, and we're going to have to work, solve those problems as we go along. But yes, it is a problem, and security is a big factor. But it's the same as adding a compute node to your system, right? You have to protect it. So we're running an operating system. We can run firewalls. We can run all sorts of whatever mechanisms we have to protect ourselves.
Another add-in card with another 16 ARM cores to be the firewall.
Well, it is what it is, right? But yes, you're absolutely right. It's a problem that needs to be tackled, in all its dimensions. So we're adding maybe a little bit more complexity because it's a potential point of attack. That's true, but it's something that you can't stop progress because of that, right? You have just to work harder on the security side.
The other comment to make, because this encryption is actually it's hardware accelerator. It's in silicon, so it doesn't involve the CPU to run it. So it's a lot more faster. It's line speed at much lower power consumption.
The only thing I was going to add to your point is that there's probably some pretty clever things you could come up with certain customers. I mean, if, for example, you're doing it on a completely air gap separated, very local wire, essentially, now you provide another layer of security from an attack surface, and you're also creating something that doesn't actually use network resources, right? Depending on what sort of data flow it needs, you could just have a local LAN just for the drives. It never connects to anything.
Are you thinking like a honeypot or something like that?
No, I'm saying in this case. Well, no. Now that's a really nice conversation to have. But no,
like an isolated
I'm talking about a completely air gap separated. Just the whole world doesn't exist. It's a wire for
John,
them.
You're thinking more like an isolated SAN that only carries SAN traffic.
Yeah.
And so we have an isolated image VLAN that only carries image files.
The honeypot one.
So that is a good point. From a physical point of view, any attack will have to go physically through the host. So it's got to go somehow through the NIC into the root complex and into the host via applications, whatever it is, to get physically to our drives. Now, if you can protect that, awesome. But you add more complexity to a system, always security is a problem. It's easy to design. It's very difficult to protect against hackers, right?
So you said that you know about that. So when do you think you'll be able to address that?
Well, when it's deploying, you mean multiple of the, as we expand with the customer, basically, because we don't do
in this case,
right?
our customer is actually helping us with that side of the application, and we'll be able to leverage.
When somebody says we'll buy several $1 million worth.
Exactly.
Yes, thank you.
No, so security without any context is a useless debate. Everything is about the threat model. So if your customer has a system that operates inside a vault and it's not connected to the external world, who cares? Right. If it's a Swiss cheese connected everywhere, then it's a problem. So really, we're going to have to see, okay, what are the customers that are going to consume this in high volume, and talk to them and say, okay, what is your threat model? What is potentially what are we adding in terms of threat, and then work with them.
Yep.
Realistically, I mean, I'd love to have like a canned, response, but in reality, that's what's going to happen.
I think when a customer wants to buy enough product, we'll do it as a perfectly reasonable response.
I appreciate that. Yeah. And in this particular instance, of course, when we're talking with this particular customer, they don't really care about the data itself that's being delivered to the end customer because it's a movie stream. It's content that somebody can get a hold of. It's not really that much of value to them from that perspective. It's all the metadata they're managing to identify who they are, when they watched it, how often they're watching what, that really comes into play.
And to know that
it's a different.
I've been watching kids
each
stuff.
application use model. Again, this platform is so open. It's so scary to try to figure out what the next best thing to do with it is.
Yeah, I just cannot see any real challenge here, because it seems to me that when you deploy that, you're just going to apply the same, let's say, network security principle that you have. You're going to separate your management network.
Yep.
You're going to kind of ring fence things to make sure that only authorized people can access it, only the hosts are going to see the devices and so on. So
Exactly.
I don't see a big challenge here with security itself. Might be more about where the data might be stored and all.
Right.
And it depends on the quality of the data, I mean, what you have, what you're processing.
Yeah, absolutely. Appreciate that.